Okay, it's coming good. Yeah, so now, okay, so this is the picture that we should have in mind about Dirichlet series. This is the general picture, but it's good to have some examples also. Yeah, question, yeah. Okay, yeah, that's an excellent question. I don't know the answer. That's good. Why don't you explore the question and let me know next lecture? I don't have any answer to that. Yeah, that's an excellent question. Yeah. It sounds like a question that has been answered to me, but okay. But that's a very excellent question. Yeah. Yeah. Now we will see actually an example of that series, those series, right away. That's our example one. So EG1. So what's the simplest type of non-trivial or whatever Dirichlet series? Give the simplest example of Dirichlet series. It's a zeta function. It's just, that doesn't get as simple as that. So zeta s equal to sum 1 n to the s, and from 1 to infinity. I mean, we wrote z, but I hate to write z for this analytic number theory stuff. I really like to write s, as Riemann wrote s, I believe. Zeta of s equal to this one. So this is obviously the Dirichlet series. Now, so what is rho and what is rho prime for this one? What do you think is rho and rho prime for this? So the abscissa of convergence, or the vertical line. Yeah. 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 The other one is 2. Yeah.
I know it's a bit after.
They're good after 2. Yeah.
Oh, it's 0.
Rho is 0, rho prime is 1. Okay. So let me write these lists. Rho equal to 2. Rho prime was not committed. Rho equal to 1. Oh, wait a minute. Yeah. Rho equal to 1, or what was rho? Maybe you meant rho prime equal to 1, rho is equal to 0. Is that what? Because rho prime is bigger than equal to 0. Rho prime equal to 1, rho equal to 0. Is that what you said? And any other takers? Yeah, that's relevant. Yeah, for sure. And guess both 1. Yeah, indeed. Both are equal to 1. I mean, this is, as I said, this is an example where actually the answer to your question is positive. Rho is equal to rho prime equal to 1. Let's see why. You see, first of all, this guy is convergent here, right? This guy is convergent here because of p-test. In fact, absolutely convergent because of it. Because now you have to deal with S complex also. No? But anyhow, if you prove that it is convergent on real numbers, then you don't have to worry about absolute. If it is convergent on real numbers here, by the theorem we proved, you know that it is convergent all the way up and down to the right. So you don't have to worry about complex issues at all. Okay, so here. But now I claim that it cannot be convergent any point here. Not convergent even any point here, or less than. I'm saying it is divergent at all points where real part is less than 1. Why is that so? Well, the proof is very easy. If it is convergent at some z0, where real part of z0 less than 1, okay, like that, then we know that there's going to be a real number, that this guy is going to be convergent here for S real, S bigger than real part of z0. It should be convergent. But you see that this series cannot be convergent for any S real less than 1. P-test. That's it. So rho is equal to rho prime is equal to 1. That just simple observation proves it. That's the power of the theorem. You see, it frees you from this complex plane complications. It really brings you down to checking on the real line. So this is very useful. So example 2. Let's look at the alternating version of this. Maybe eta of S equal to 1 over 1 to the S minus 1 over 2 to the S plus 1 over 3 to the S minus 1 over 4 to the S, so on. So what is rho prime in this case? In this case. So rho prime is about absolute values, right? Let's take absolute value of these things. I mean, these negatives becomes positive, and it's 1. So rho prime is definitely 1. And you take absolute value on the real S real less than 1 does not converge because of p-test again. So rho is definitely 1. We know that. Now, what about rho prime? Okay, so sorry, rho prime is 1, I meant. What is rho now? Rho is 0, yeah. Rho is equal to 0, in fact. And the reason for that is this famous alternating test. The alternating test was that if the general term goes to 0, what was it? What was the thing? Was it decreasing? Is decreasing and is alternating in sign, is going to 0, then it is convergent. So I guess by alternating test, sigma minus 1 to the n to the s, and from 1 to infinity converges for at least s belonging to R and s bigger than 0. That's what the alternating test tells us. And it's certainly not convergent for s equal to 0 and for s less than 0, because for s less than 0, the general term even doesn't go to 0. For s equal to 0, you have 1 minus 1 plus 1 minus 1 plus 1, which is divergent. Okay? So you know that then as a result, rho is equal to 0. So that has a very interesting thing. So this is like 0, this is 1, here is the thing. And here is what we call conditional convergence, I believe. Yeah, in analysis, conditional convergence. It's conditionally convergent only. It means it's convergent, but it's not absolute. So next question, where this function is holomorphic? Where this function is holomorphic? After rho prime, yeah, it doesn't have to be after rho. Oh, you say I'm confusing rho and rho prime. I meant, yeah. Yeah, the absolute convergence was not relevant for holomorphicity. Everywhere, yeah. This function is holomorphic for real part of S bigger than 0. Okay? But the zeta function originally is holomorphic only in real part of S bigger than 1. Of course, it's a question if the zeta function is convergent at these points or not, because this is kind of critical line, right? We know that it is divergent at all other points below the line. That's for sure. That we know. But on the line, if it is convergent or divergent, is a delicate matter. We cannot answer it right now, maybe in 10 minutes. It needs some elaborate, rather elaborate consideration. It's not too bad. But you just pay attention. Same, now if you look at here though, at real part of S equal to 0, this function is totally divergent everywhere here. Because you get what? You get 1, minus 1, plus 1, minus 1, this divergent. So you see different types of course, for zeta, you know that S equal to 1 itself is not convergent. Because that's harmonic series, right? So that's, but we don't know if it is convergent at all these funny points. And what is your guess? Just some of them diverges. Yeah. Any other? Yes. It's very hard to guess here. Really. It's not a fair question. I agree. I mean, it's kind of how can we? So we have no clue just by looking at the question. You know, because these complex powers can be very, very complicated, arranging themselves like that, n to the power 1 plus I. So 1 plus ti for different values of t, right? And yeah, that series over here, I mean, this series over here is like this series. Yeah, I mean, this is not the. But this we know for sure. That's the pole of the zeta function. Yeah, S equal to 1. But what happens? Yeah. We'll see that actually it converges at all these points. That's quite interesting. Am I right? Yeah, I think I'm right. What's that?
Like it has
This point? No, it's not removable at all. That's a real singularity. We'll see. Okay, I'm just teasing your appetite for things to come. Now, okay, so now let's go back to generalities again and define some ordinary. I think Serre calls it ordinary Dirichlet series. So this is what most people really consider when they think about Dirichlet series. They think about such things. AN belonging to C. These are the type of Dirichlet series we will be most be working with. So now the proposition is that if AN are bounded, so here's a useful proposition. So let's call it f of s. If AN is less than or equal to m for all n, then f of s is convergent for real part of s bigger than 1. And of course, holomorphic. I don't even have to say that now. Proof. Okay. Well, I mean, if to see that, you just use absolute values, right? It's just, well, what is it? I mean, sigma absolute value of an over n to the s. I mean, this is less than or equal to sum. I mean, this guy's m. And we know that this is, of course, convergent for a real part of s bigger than 1. This is like the estimate they use for zeta functions and all that. So this is convergent. So such series that has this condition that ANs are bounded, they are always at least holomorphic in real part of s bigger than 1. Okay. So now we can introduce zeta functions and L functions. We have introduced already zeta functions. So this is Dirichlet L functions or L series. So so again, let's fix n bigger than or equal to 2. Let phi be a character modulo n. So we are going back to the beginning of today's lecture. So there's a character on Gn, right? Etc. So I mean, this is a Dirichlet character modulo n. Then L of S and chi, let's define it to be sum chi n divided by n to the s, right? And from 1 infinity. So this is the Dirichlet L function or L series attached to this character modulo n. For any n, you can do such things. And of course, by this thing that we proved, this guy is holomorphic in real part of s bigger than 1, at least, right? Okay. So one thing that we have to recall is that this chi is fully multiplicative. I.e. chi of nm is equal to chi m for all n and m in Z, right? This is what I mentioned, at least, that they enjoy. And the multiplicative condition was just one condition. It was that chi of nm is equal to chi and chi m only if n and m are relatively prime, only for those pairs. If n and m is 1. Okay. So we have two concepts. We have to be very careful to distinguish them. Fully multiplicative arithmetic functions and multiplicative arithmetic functions. So multiplicative is a weaker condition. Fully multiplicative is the natural condition. I would call it multiplicative, the other one weakly multiplicative, but people prefer to call it. So here are some examples. Let's look at the Euler's phi function. Is this multiplicative or fully multiplicative? Or none? What can you say about this? Phi of n. Huh? It, not fully multiplicative, you're saying, but multiplicative. Okay, that's an answer. Any other answers? No answers? Yeah, indeed, this is the correct answer. It's multiplicative, but not fully multiplicative. Is multiplicative, but not fully. So proof. So what we want to show? We want to show that phi of mn is equal to phi of m, phi of n, if m and n are relatively prime. How do you prove that? Yeah. Okay. Oh, yeah. Yeah, well, I mean, so deriving the general formula really depends on this also to show that it is multiplicative. So this is basic algebra. I taught algebra last semester. So yeah, last semester, I think so. I'm still fresh on that. Huh?
That's before last.
Before last semester, okay, yeah. So I already forgot what it when I was teaching. Yes, that's right. Yeah. So how do you prove this, though? There is an elementary proof for sure, but a good proof is to use Chinese remainder theorem. So what does Chinese remainder theorem say? You see, so let's see. We know that phi of n, okay, is the order of the multiplicative group of z mod and z, right? Is the order of multiplicative group of this guy. But if n and m are relatively prime, you can decompose as z over mz cross z over mz. Only if m and n are relatively prime, not otherwise. So what do we have then? We have this isomorphism of rings. This is isomorphism of rings. So what does it mean? It means that if I want to take invertible elements there, some element is invertible if and only if the first component is invertible and second component is invertible, because we are just multiplying pairwise, right? So this is going to be this, cross that, and then of course follows, right? And you can convince yourself that this is not fully multiplicative by just giving example. Like phi of 4 is not equal to phi of 2 squared. You know that. Phi of 2 is 1, but phi of 4 is 2. It's not the square of that. And so on. By the way, you know that phi of p is equal to p minus 1. And what is phi of pn? What? You mean pn minus 1?
Yeah.
Is that what? That's
That's what I tried to say. I don't know if that's what I did say.
yeah, so I almost heard you, yeah. pn minus 1. Maybe it is correct, but I don't know. I have to check. I can't. Is this correct? Okay. So you are responsible for this. You know, if some bridges break down tomorrow, you know, based on this, I don't know. I won't be responsible. So maybe I just put with some caution, but that's, I believe you. This is correct. So using that, then we know everything, right? Because so you can just write phi of any number as p1 and 1, p2 and 2, so on. You can write it as then p1 and 1 minus p1 and 1 minus 1 times da da da. Using multiplicativity, weak multiplicativity. So that's pretty good. Now, there is a result, which is a Euler product formula for such things that I want to mention, and then we are finishing in 5 minutes. That's it. Yeah. The last thing we want to do today, now that we are at it. Oh, there is another one, which is maybe I mentioned, so that's kind of interesting. So there's another example. This is Ramanujan's tau function. So it is defined from sum tau n q to the n from 1 to infinity is equal to q times product of 1 minus q and n squared, and from 1 to infinity. So you might say, okay, what? I mean, okay, so first of all, this right-hand side is convergent for absolute value of q less than 1. You know why the right-hand side is convergent for absolute value of q less than 1? It is an infinite product, right? So you have to use the theory of infinite products. It's an infinite product. So you better know some criterion for convergence of infinite products. That's important. And what is that? Okay, so I don't expect you to remember, but from you can take, yeah, indeed the proof starts by taking log of these terms and writing estimates based on that, but it's good to know the final result somehow, right? I mean, yeah, so the final result is that indeed this product of 1 minus alpha n is convergent. So imagine these guys are less than equal to 1 in absolute value. So they're never equal to 1. If and only if the sigma is convergent, right? Oh, no, that's not sigma. Yeah, that's not what I have. Yeah. Product, yeah. Not alpha, n equal to 1 to infinity. Convergent if and only if sum alpha n This is something maybe you have seen in complex analysis, Weierstrass infinite products, expansions, this sort of thing. So this is kind of. So this is, I believe this is correct. And no, it is correct. And it's extremely useful because working with infinite products is kind of unintuitive. It's, yeah, but with series, humans have better understanding of series than products somehow. Okay, so this is obviously then you can apply this criterion, the test, this infinite product, sigma qn is convergent for absolute value of q less than 1. So this is convergent. So this is convergent, is a holomorphic function in Q, so you can expand it for absolute value of Q less than in Taylor series, and this is what. So that's a roundabout way of defining these numbers tau n's. These are Ramanujan numbers. There are other definitions for them, but now the thing is, this is a multiplicative function. Not fully multiplicative, but it's multiplicative. I don't know. I didn't check Serre what he says. Maybe he just gives a proof. I'm not sure. Maybe he just mentions it, or maybe this is just I got it from in my notes from some other sources. I'm not sure. Does Serre say anything about it? Yeah, I don't know, because if he mentions it at one stage, certainly I'm almost sure that he would give a proof. Otherwise, he wouldn't talk about it. Just mentioned it. Okay, so I think we can prove it at one stage. Yeah. All right, so I think it's a good time to stop now, and I just stop the video. Let me get, oh yeah.